Alright, in the earlier section, 6.2.1, we talked about foot of the perpendicular from a point to a line. Correct? Then this is the foot of the perpendicular. This is the foot of the perpendicular. Now 6.2.3 deals with a foot of a perpendicular from a point to a plane now. From a point to a plane. See, there's a plane and we draw perpendicular. Easily explain if we just use an example. Let's take a look at the example. Example 7. I have a point P with position vector 4j. 4j is not difficult, 0, 4, 0. So I would usually like to label it like that. P is 0, 4, 0 with coordinates so that I don't confuse myself. Because O is somewhere out there. O. I don't even bother myself with O. I don't need to label O at all. But it will be dangerous if you label O here. It will be dangerous worse you label O, I don't know, on the plane or whatever. But the fact is we do not know where is O. So we better don't label. And when I label, because you see O, you're tempted to label, but actually you don't know where is O. Alright? So this plane has equation r dot 201 equals to 4, which means the normal is 201. Now, do I know the normal vector n is pointing upwards or downwards? I have no idea. Whether the P is on this side or on the other side, or on the other side of the plane, I don't know. Just draw. Alright? It doesn't matter. So the question asks us to find the foot of the perpendicular F, which is the foot of the perpendicular from P to the plane. Method A. So first method is the idea of solving intersection between a line and a plane, which we have done before. Intersection between line and plane, you can solve simultaneous equation, we are done. So, but which line do we have? Simple. Do we have is this line PF? Is this line PF? Do we have the equation of PF? Let's think carefully. I have a point, I have a position vector of a point, which is P, no problem. Do I know the direction of PF? The direction of PF is actually the normal vector, isn't it? Because PF is perpendicular to the plane. So, therefore, the equation of the line PF is this. This is 1 point, 0, 4, 0 is 1 point on the line here. Direction vector is 201 because this is the normal vector. So maybe you may want to write down this is the normal vector of the plane. Makes perfect sense. Therefore, we know the equation of line PF. Now, do we know the equation of the plane? Of course we do. It's given there, here. Here. So therefore here. So all you need to do is to solve simultaneous equation. Done. You have done in vectors 5. You have easily done that in vectors 5. We will sub 1 into 2. You will get a 0, 4, 0 plus S 201 dot 201 equals to 4. And you take dot product, blah 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 blah. Yes. You will get this 0 plus 5s equals to 4. S equals to 0.8. Now, once you get s equals to 0.8, what do you need to do? You just substitute s equals to 0.8 into here. Equation of the line. Quite easily, we will get the answer, which is OF. Remember, the question asks for coordinates. Remember CT1 asks for coordinates. You better give in coordinate form. We get this. My preferred method is this. It's quite easy. It's not difficult at all. I think it's quite easy. And my preferred method is to solve simultaneous equation. Of course, some of us may know by now there is a method B called projection. Now let's take a look at the same diagram again. Let's do the same diagram. I have a point P, which is 0, 4, 0. Yes. I just want to know what is this. I want to know what is F. I know N is 201, correct? is parallel to 201, not a problem. I know this vector, which means that this vector PF is parallel to 201. If I can randomly find a point A on the plane. Now, let me give you this one. R dot 201 equals to 4, right? This is the equation of the plane, right? Without looking, let's look. Just zoom in like that. Can you tell me what is a possible point that lies on this plane? You may tell me, oh, I know, 200. Why? Because when I take 200 dot this, 200 dot this, I get equals to 4. Any pair of x, y, z that can satisfy this, it will be a point on the plane. So, for convenience, I just take 200. Now, of course, you don't want to have 200. Yes, of course you can. You don't like 200? Can, of course. Can you say 0, 0, 4? Also can. As long as it satisfies the equation, we are good. Or you don't like, also can. You like 1, 2, 2, also can. Right? As long as it satisfies the equation, you are good. So, the point is, we just find any point. And for convenience, now I can now explain what. For convenience, we have taken the point A, where A is the point 2, 0, 0. There's nothing magical about the point A. As long as a point on the plane is good enough, you can put 0, 0, 4, it doesn't really matter. Later on, you find the answer is the same. Okay? So let's assume a point 2, 0, 0. Now, if I can project the vector, PA onto this vector 201, I will get PF. I repeat one more time. If I take this vector PA project onto this vector 201, I will get PF. Now, it needn't matter whether this 201 is pointing upwards or pointing downwards. Again, I say, I do not know this 201 actually is upwards or downwards. Do you know? I don't know. So it needn't matter. As long as you project PA, if you learn your projection well, you may want to refer to the notes, your notes on projection. PA project onto this vector, you will get PF. Not FP, it's PF. So, can I then find what is PA? Can. PA, this one, maybe I may want to write this. This is actually OA minus OP. Okay? I think it's quite easy. We can do that. Then we use the projection formula. PF is just PA dot n hat. Yes? Then we just write it down. I don't think it's difficult. What is PA? PA is 2 minus 4, 0 dot n hat 201 1 over root 5 201. Yes, in the end, you get 0.8 201. So, now, I have found what is PF. Let's take a look at the diagram here. I have now found what is PF. Yes, I found what is PF. So, what do I want? I want OF. Yes, OF is now OP plus PF, and you get answer. So, the idea is to use projection to find a vector. Like that. Yes, to find a vector here. It needn't matter whether ultimately I find PF or FP. Yes, it doesn't matter. You could have, maybe I could say alternatively, I could have found FP equals to AP dot n hat. Now ultimately, it's fine. If you found FP, could you still have found OF? I mean, after that, you can still find OF. No, not a problem at all. not a problem. So as long as you find PF or FP. So the point that this is trying to make is that whether we project, if you project PA, let's look here. If you project PA on N, then you will get PF because the direction of the shadow follows the object. So if the direction of the shadow is this way, you PA project onto the vector, you will get PF. But if you take AP the other way, you take AP project onto the vector, on the normal vector, you will get FP. I repeat one more time. If you get this one, AP, if you project AP onto the normal vector, you will actually get FP, this direction. Get it? So we must be very careful. What have you found? In our case, we have found PF. You could have found FP as well, but it's the other way. So anyway, we have found F in another way. Summarize again. There are two methods to find the foot of the perpendicular from a point to a plane. One, I find it easier if I can solve simultaneous equation. Find equation of a line, solve simultaneously. Done. Correct? Second is to find a point on the plane. In this our case, I call it 2, 0, 0. Then project our PA onto PF, onto the vector, onto the normal vector. I'll get PF. Then from there, I can find what is OF. Slightly longer, I feel. But it's okay. It's up to you. Let's move on. How about reflection of a point in a plane? Previously, we talked about reflection of a point in a line. Now we talk about reflection of a point in a plane. That means on the other side. It's a point, it's a plane. I want to find the other side, the reflection. So, the idea is exactly the same. It's actually very similar to the reflection of a point in a line. In fact, the concept is exactly the same. If I can find the foot of the perpendicular, if I want to find the reflection of this one onto the plane, then I want to find P prime, which is a reflected point. All I need is to find the foot of the perpendicular first. I repeat, you find the foot of the perpendicular first. Once you have found the foot of the perpendicular, the relationship is just this. This is ratio theorem. Exactly the same as the reflection in a line. So, we use example 8 to illustrate our point. The position vector of a point P, this is exactly the same example 7 if I'm not wrong. Yeah, similar to example 7. Same, exactly the same. Same as example 7. So how is it 4J, right? And 201, right? Find the position vector of the point of reflection in the plane. So, I think I will draw a diagram. This is P. This is P prime. P prime. Alright, here's P prime. So, I have found earlier what is F foot of the perpendicular because it was the same equation. This is pi. From equation, this is the F is 1.6 for 0.8. Right? Yes. So by ratio theorem, OF is the midpoint. F is the midpoint of P and P prime. I will say OP plus OP prime over 2. So of course you make OP prime the subject. I will get 2OF minus OP. Then we just substitute in. I get 1.8 251 minus 0.40. And then you get 3.2 for 1.6. This is for earlier part, the OF is from earlier part. OF is here. Or maybe I shouldn't write this one. Your OF earlier was this. Otherwise, you don't know where I got my 2 OF from. I just write 2, 1.6, 4, 0.8. Like that better. Yes, minus. Yes, that's it. Nothing fantastic, it's still the same. Alright? Just a few two additional questions. How would you find the equation of L2, which is a reflection of the line L1 in another line? Whoa. What I'm trying to say is this. Think. Let's say I want you to find, this is L, I call this L. Okay? I want to find the reflection. How do I reflect L1 in this line? So effectively, the reflected line is this one. This is L2, which is the reflected line. Yes? So you got 3 lines basically. The first line, and then you want to reflect this L1 into this. I tell you concept. Okay, I'm not going to show an example. The idea is this, very simple. First, I find the point of intersection between between L and L1 first. Okay, I call this point of intersection P. Yes, I call this point of intersection P. Now, P obviously must also lie in L2, which is the reflected line. As long as I can find one more point, A prime, I'm good enough. I join A prime to P, I know equation of line already. If you know your equation of a line well enough. How do you find A prime? A prime, essentially, I can let a point A, randomly find a point A in the line L1, reflect A in this line L, I'll get A prime, I'm good. Now we think, how do I reflect a line in a plane? Isn't it the same idea? Isn't it the same idea? Maybe you may want to discuss with your friends, ask your teacher, how do you think it can be done? Okay, we can discuss this in the next lecture.